Hello, Science 20s. Today is going to be a two-part lesson. First, we're going to start with a little demo looking at the reactivity of three different metals. Then we're going to move on and try to figure out what the terms spontaneous and non-spontaneous reactions mean. So let's get started. Well, one of the first things most people tend to think of when we think of metals is they want to talk about gold. Why is gold so important? Why is gold so precious? Why is gold so amazing? We all know I can pound it with a mallet so it's malleable. I can hit it into sheets. We all know how ductile it is. I can heat it up and I can stretch it into wires or strings, or I can make rings or jewelry or necklaces out of it, or links for chain. We know it's very stable. Gold atoms have a very strong tendency to keep their electrons, stronger than all other metals. What I'm going to do is we're going to do our little demo. We're going to teach our lesson, and then we're going to come 180. And at the very end of the lesson, I'm going to prove to you why gold has the tendency not to react like other metals, why it has a tendency not to tarnish, not to corrode like other metals do. Well, we're going to do a little bit of a demo. Now, I videotaped the demo. I'm going to do it. I'm going to talk through it, though, because volume doesn't work on it. But we're going to walk through this demo that I set up for us. So in this experiment, we're going to compare three metals, and we're going to put them in here as we go down. So the three metals we're going to compare is I'm going to put silver pieces in these three wells going down. Then next to them in the middle well, I'm going to put three zinc pieces going down. And then in the very first column, I'm going to put three pieces of copper. So we have three solids. Across them, I'm now going to mix them with three solutions. I'm going to mix it first with, this is going to be silver nitrate solution. So I'm going to put a few drops of silver nitrate solution in each of the three wells that already contains the metals. I'm then going to take copper 2 solution, and I'm going to put it in each of the three wells across the middle. Sorry, excuse me, that's zinc solution across the middle. And then on the top one, the blue one is copper 2 solution. Looks like ground up Smurf juice. I'm going to put copper 2 solution across the top. And what we're going to do is we're going to wait for a few minutes for these guys to react. Once they've reacted, we're going to try to figure out which ones actually had a reaction. If they had a reaction, it's going to be obvious. And if there's a reaction, we call that spontaneous. It could be a color change. It could be that they got bigger and looks kind of like a blob. It might be that they have crystals forming. This is going to be really obvious. If it looks like a color change, then it will be a color change. If it looks like it's grown and it's gotten blobby, it will look blobby. This is not going to be something where you have to squint and go, I think it might have changed. Well, if we look down the column here for copper, copper solid did not react with copper solution. Copper solid did not react with zinc solution. But copper solid did react with silver solution. And you can see that it turned black. And if we could zoom in, it would actually look kind of like it had like a little caterpillar. It would have little feelers. Zinc, however, did react with copper solution. It turned black. Zinc solid did not react with zinc solution. Zinc solid did react with silver solution, and it'll actually looks like it grew. It became a giant blob. My expensive pieces of silver didn't react with copper solution, didn't react with zinc solution, and they also didn't react with silver solution. So my silver pieces, my chunks of silver, didn't react with anything. What I would like to do is let's take this information now and fill in my table. Let's write down what we actually saw occur in this reaction. So when we did this, we saw copper only reacted with silver solution. Oh, I got to go back, grab my pen. Copper only reacted with silver solution, didn't react with these two. Zinc reacted with copper solution and with silver solution, didn't react on that one. And silver, my expensive silver, didn't react at all at any time. Well, what I would like to do is let's add up how many reactions we had. So for copper metal, we saw one reaction, one check mark. In zinc metal, we saw two reactions. And my expensive silver had absolutely zero reactions. It was really boring. Now let's also look at the solution. So my copper solution, the blue solution, had one reaction. The zinc solution had absolutely zero reactions, and my silver solution had two reactions. Well, if you think about this, this is kind of interesting. Silver metal didn't react at all. It was boring, but silver solution had the most reactions at two. Zinc metal had two reactions. It reacted the most, but zinc solution didn't react at all. There seems to be some connection here. If the metal is good at reacting, its solution is poor at reacting. If a metal is poor at reacting, its solution is really good at reacting. And that's what happened with silver, right? Like my metal was really bad at reacting, didn't react at all, but my solution kicked butt. So let's clear this. And let's use this idea to talk about some of this stuff. So, which ion reacted the most? Well, that's easy. That was my silver ion. Which ion reacted the least? So if we go back, that would have been my zinc ion, didn't react at all. So using this idea, let's take my three ions and put them in order. Silver reacted the most. Copper reacted second by reacting one time, and zinc ion didn't react at all. It was so boring. Well, if we write out these half reactions, these reduction half reactions, silver ion turned into eventually silver. This was our piece of silver. Copper ion turned into copper solid, and zinc ion turned into zinc solid. Well, these are going to be reduction half reactions, so let's balance them. One silver, one positive plus one negative electron, no charge, no charge. Exactly what we did yesterday. Again, two positive plus two negative electrons, no charge, no charge. Two positive plus two negative electrons, no charge, no charge. So all of these are reduction half reactions. Well, what I want you to see is there's a pattern to these. If you go back and you look at our table, silver ion reacted with copper solid and zinc solid. Huh. They reacted with solids below them on this table. Well, let's look at something else. Copper solution, the blue stuff, it reacted only one time. It also reacted with zinc solid. So it reacted below it. It seems like if you're up high on the left, you react with some piece of metal below it on the right, there's going to be a reaction. And that is what the rule is. If it is downhill, when you read left to right, if you read and it's going downhill, there's going to be a reaction. And we call that spontaneous. So let's take a look at this. Now, before I can take a look at anything else, we have to look at these definitions. So if we take a look, a reducing agent, new word, causes reduction. It causes reduction by donating or losing electrons. Now, you know this idea of losing electrons from yesterday. Losing electrons is the definition of oxidation. Leo, losing electrons, oxidation. So reducing agents and oxidation goes together. They pair together. Reducing agents and oxidation go together. And I like to say oxidation is the same as a reducing agent. Well, that's very similar to an oxidizing agent causes oxidation. Well, that means an oxidizing agent gains electrons. Well, gaining electrons, grr, that was our definition of reduction. So oxidizing agents and reduction goes hand in hand. They're the same thing. So if something is being reduced, it is also our oxidizing agent. Well, there is a really, really easy way to remember this. And the easy way for us to remember this is the learning track. I like to think of the learning trick of thinking of Shrek eating spaghetti. We all know Shrek is an ogre, and we all know a type of spaghetti sauce is ragu. So, if I remember ogre, oxidizing agents get reduced. So, if something is reduced, It is also my oxidizing agent. Oxidizing agents get reduced. Ragu, reducing agents get oxidized. So if something is oxidized, it's going to be my reducing agent. Oxidizing agents go hand in hand with oxidation goes hand in hand with reducing agents. Reduction goes hand in hand with oxidizing agents. Ogre, ragu. That's my learning trick. Now, what does that actually mean to us? Well, that means if I take a look at this table, which by the way is in your data booklet and it's on page 4 in the top right left-hand corner, I'm going to take this table and I'm going to find the substances we did in the lab today. We had silver ions, we had copper ions, and we had zinc ions. We had silver, we had copper, and we had zinc metals. And what we noticed was, and here's the rule I want us to get to, silver reacted with anything below it. Silver ion reacted with anything below it on this chart. Silver ion, if we go down, reacted with copper solid. Silver ion, if we go down, reacted with zinc solid. That is also true if I think of copper. Copper didn't react with silver, that's going up. Copper ions didn't react with copper metal, that's going across. It only reacts going down. Now, the thing you have to do in your data booklet is, and I allow you to do this, these are all written as reduction half reactions. I know they're reductions because think of the saying from yesterday. Leo the lion says, grr. All of these equations are gaining electrons. The electrons are all on the left-hand side, gaining electrons, reduction. Here are 20 examples in our data booklet of reduction half reactions. It even tells me reduction. Please don't ever get these wrong. If you have an electron on the left-hand side of the arrow, of course it's reduction. You have 20 examples here of reduction half reactions showing me arrows on the left mean reduction half reaction. Okay, well, we already know from the previous slide, another way of saying reduction is saying oxidizing agent. So I like to, on this table, put SOA at the top left-hand corner. So AU3 positive is the strongest thing to get reduced, but it's also my strongest oxidizing agent. And my oxidizing agents get weaker as I go down. Most strong, most reactive, least reactive. Down here, if I read this table now going backwards, notice my table. If I read from lithium going across, I now am losing all my electrons because all my electrons, if I read from right to left or on the right-hand side, they're all on the product side. This is oxidation. So down here is my strongest reducing agent. Strongest Ra. And remember, Ras go with oxidation. They pair together. So this guy's my strongest reducing agent. They get weaker as we go up. So strongest reducing agent, bottom right corner. Strongest oxidizing agent, top left corner. I really, really, really badly want you to write that onto your table. SOA, top left corner, SRA, bottom right corner, which means if we're a stronger oxidizing agent than we are a reducing agent, it's going to go downhill and you saw a reaction. We will call that spontaneous. So this is the end of video 1. Please make sure you stop, catch the notes for video 2, and finish watching part 2 of the video. Thank you.